because of the interaction term, this Hamiltonian is not separable, and we have to use approximation methods. And the very important approximation method is called the variation method. Variation. To vary means to change. So here we are going to be changing something. By changing something, useful results are going to be obtained. This method is based on the variation principle. And to express the variation principle, let us call H to be a time-independent Hamiltonian. All our Hamiltonian expressions are time-independent in this course. Let E1 be the lowest exact eigenvalue of H. Then, given a normalized wave function, which we call psi trial, using the given psi trial and the given H, we can calculate this integral. In this expression, everything is known. H is explicitly known. For example, here, this is completely known. By assumption, this function, psi, which psi trial, is given to us here, given a normalized psi trial. So, there are no unknowns in this integral. Limits are over all space. The result of this expression is going to give us a number. And that number will have what kind of unit? Unit of H. What is the unit of H? Energy. Hamiltonian is kinetic plus potential energy. It is energy. So this value we call E trial. It's an energy. I attach the trial here because its value depends on which function I substitute for psi trial. Now, you imagine all possibilities for the psi trial. There are infinitely many such possibilities for psi trial, which means there are infinitely many possible values for E trial, for the result of this integration. Now, the variation principle states that all of these infinitely many E trial values are necessarily larger than the lowest exact energy of the system. Exact ground state energy. Lowest eigenvalue means the ground energy level. So, E trial is larger than E1. This is the variation principle. So no matter which expression for psi trial you use there, the number for E trial is going to be larger than the exact ground energy. This is the variation principle. If you happen to guess the exact solution of this problem, if you happen to guess this psi, which satisfies this expression with E1 as the energy, which means the exact state function, then that calculation is going to give you E1. But this is an exception. There are infinitely many possibilities for psi trial. Only if somehow you guess the exact psi, then you are going to obtain E trial to be same as E1. So this expression is written like this. There is a possibility for using the exact state function in that expression. In that case, E trial will be the same as E1. But the normal case is we don't know the exact psi, and therefore our E trial values are always going to be larger than exact energy. So the procedure goes like this. We write down explicit expressions for psi trial. In other words, we try to guess psi trial. We substitute in this expression and do the integration. We find a value for E trial. We know that this value is going to be larger than the true value. Then we try to find better psi trial. And we do this we try to do it in a systematic way. We introduce parameters like coefficients, which are initially unknown coefficients, and then we minimize the E trial with respect to these parameters, because we know that whatever we do, we will never go below E1. We are going to stay above E1 all the time. So this problem is converted into a minimization problem by introducing some adjustable parameters in the expressions for psi trial, and then choosing the values of the adjustable parameters using the minimization criterion, which means minimization is a maxima minima problem. We take the partial derivative of the E trial with respect to each unknown parameter, set it equal to 0, and then find the values of the parameters and use those parameters in psi trial to get the best value for the E trial. The best value for E trial is still above the exact energy of the system. So if we can succeed in lowering the energy as much as possible, then we are approaching to the true value from above, because the lowest value is here. Whatever we do, we are always above it. We try to press it down to minimize it, and if we succeed in pressing it down strongly, then it means we have approached the true value more correctly. That's the procedure. Today, such calculations are done using computers, but the main technique, main approximation method is this. It depends on this principle here. So it's a very important concept for those of you who will pursue quantum chemistry in your studies. Okay, now, in selecting the psi trial, or in writing down expressions for psi trial, we make use of some known information about the solutions of the Schrödinger equation. This doesn't mean we know such properties after solving the Schrödinger equation. No, because our purpose is to get an approximate solution to the Schrödinger equation. But without solving the Schrödinger equation, using some symmetry properties of the Hamiltonian, it is possible to extract useful information about the solutions of the Schrödinger equation. And the main idea here is in doing this is, if there is an operator A which commutes with H, the exact H, then we know that the operator A and the exact solutions psi are the same set of solutions. In other words, the commuting operator A and Hamiltonian H have the same set of eigenfunctions. Solving the eigenfunctions of H is very difficult, as we said here. That's why we are resorting to approximation methods. But it turns out that there are certain operators A whose eigenfunctions are more easily found, or in fact they are known. So we use that information for the simpler operators which commute with Hamiltonian to deduce some useful information about the solutions of this problem. Now, one such operator is, for the atoms, is the total orbital angular momentum. The total orbital angular momentum of n electrons in an atom is a vector quantity defined by this expression. L1 is the angular momentum vector for electron 1. L2 is angular momentum vector for electron 2, and so on. The total angular momentum is the sum of these vectors. The z component of this vector operator, is obtained from this expression. Just write down the same expression, but using only the z components. Just like for a single electron, Lz, z component of angular momentum, commutes with L square. All right? For the total angular momentum, the same properties hold. In other words, Lz square, Lz commutes with square of total angular momentum. Let us write this. Lz commutes with L square. Remember, L square is this sum. And Lz is also the lower sum here. So it is not just for a single electron, but it is for an electron. In fact, how many variables are contained in these expressions? Each one of these terms contains two angles as variables when we use spherical polar variables. None of those terms contains R variable, the radial distance, remember, for a single electron. So there are, this expression contains 2 times n variables. This one contains n variables, the phi variables for each electron. Even so, Lz commutes with square of L. This means Lz and L square have the same set of eigenfunctions. However, their eigenvalues are different. Now, eigenvalues of L square are known. They are in atomic units L times L plus 1, where L takes the values 0, 1, 2, and so on. If you think about these values in SI units, you have to multiply this with h bar square. In SI units, it is L times L plus 1 times h bar square. This is in SI. So we are just taking h bar as the unit of angular momentum. This is square of angular momentum, so the unit is h bar square. So we just write a short expression, omitting the h bar square, but just remember that if you need it for some purpose in SI units, you just multiply that expression with h bar square to get it in SI units. Now, eigenvalues of Lz. Eigenvalues of Lz for a given L are all integers between plus L and minus L. This information about eigenvalues of L square and Lz are known. Now, Lz and L square also commute with the full atomic Hamiltonian. This is for helium, but you may take any atom with any number of electrons. Lz and L square for that atom will commute with the atomic Hamiltonian. This means that solutions of the Hamiltonian, which are the solutions of Schrödinger equation, the psi functions here are also eigenfunctions of Lz and L square. Psi functions Why? Because Lz and L square both commute with Hamiltonian, atomic Hamiltonian. Lz also commutes with L square. So we have how many? 3 commuting operators. The solutions of this equation, therefore psi functions, must be also eigenfunctions of Lz and L square, which means that psi, this means every psi, every solution of this equation is characterized by a certain m and a certain L value. For the m quantum number, I will attach a subscript as I did here. We are going to use the symbol m also for another type of angular momentum. It is called spin angular momentum. This is orbital angular momentum, but we have another type, and we are going to discuss it shortly. It is called spin angular momentum. To distinguish between spin and orbital angular momenta, we are going to use this subscript L, and for the spin angular momentum, we are going to use ms, S for spin, but the same symbol for m. Okay, so this is the situation. Now, it turns out the exact energy E are independent of ml for a given L, but they do depend on L value. What does this mean? For example, one of the solutions of the exact Schrödinger equation may have L equals 3. If L is 3, what are the ml values? According to this rule here, -3, -2, -1, 0, 1, 2, 3. Okay? Now, according to what, well, it means that there are solutions of this equation, exact equation, in which L is 3. But ML takes how many values? 7 values. L is same. For each, when ML changes, the psi function here changes. So we have 7 different functions, all with L equals 3, but differing in their ML values. This rule says that all of these functions have the same energy. Energy is independent of ML. So, there are how many? 7 ML values here. And 7 different functions are possible. All of them have the same energy. What do we call this type of situation? Energy is same, but there are many different functions. Degeneracy. So, number of ML values gives the degeneracy of the energy level. In general, for any L value, how many different ML values can you count? 2 times L plus 1. For any given L value, the number of different ML values is 2 times L plus 1. This gives the space or spatial degeneracy. Of a given energy level, which is characterized with L. Now, when L changes, energy changes. For example, if L is 4, energy is going to be different from that of L equals 3. But when L is 4, again there is degeneracy, because how many different ML values are there if L is equal to 4? 2 times 4 plus 1, 9 different ML values. It means 9 different functions in H psi equals E psi, all with the same energy. So it is degeneracy. In atoms, we distinguish between 2 types of degeneracy. One is because of the orbital angular momentum. Orbital angular motion, let us say. What does it mean? We have a nucleus at the center, and there are many electrons moving in space. The rotational type motion of these, it's not exact orbits, of course, but we know that none of the electrons are escaping. All of them are staying nearby the nucleus. So it is a, you may say, not very symmetrical rotation. It's always moving around the nucleus, but in space. Such motion is called orbital motion. And we say, for that reason, we say this is spatial degeneracy because of motion in space. There is another type which is related to spin. Now, spin is something different from spatial motion. And there we will see degeneracy resulting from the spin of the electrons. Then we will call that is degeneracy, that is spin degeneracy. All right? So just 2 types. Orbital or spatial degeneracy and spin degeneracy. Spatial degeneracy or orbital degeneracy is related with the orbital motion. In other words, with quantum numbers L quantum number and ML, M sub L quantum number. Now let us continue with spin. We have already mentioned that an electron a single electron, has two spin states. And we also stated that these two spin states for a single electron are represented by symbols like alpha, beta. We talk about alpha electrons, beta electrons. And in diagrams, we use arrows. Up arrow for up spin or alpha electrons, and down arrow for down spin or beta electrons. Now let us formalize those concepts. An electron has two spin states. This is experimental knowledge, that an electron has just two spin states. Now, these are related with spin functions. Now, when we talk about spin, we have to introduce one more variable to the number of variables of the electron. Each electron is, or a single electron is moving in 3 dimensions. So it has 3 space variables, or 3 spatial, using this word. Spatial means related to space. 3 space variables. Now, to describe the spin, we have to introduce one more variable. It is called spin variable. Spin variable is independent of the space variables. Spin variable has just 2 values. One value describes upspin, the other value describes downspin. All right? So it is, in that sense, discrete variable, but the space variables are continuous variables, if we take x, y, z as the space variables. Now, let S be the spin angular momentum. Spin angular momentum operator of a single electron. Then it has a square of S operators, and also z component of this vector. As in the orbital angular momentum, z component commutes with s square. That means they must have simultaneous eigenfunctions. Now, experimentally, it is known that there are just 2 spin states, which means there are just 2 eigenfunctions of this operator, not more. One of them is alpha, the other is beta. And let us call this symbol sigma be either alpha or beta, one of these functions. Then either alpha or beta satisfies this expression, s times s plus 1 times sigma, where s has just one value, which is 1 over 2. This means that whether you put alpha here, alpha, alpha, or beta, beta, they are both eigenfunctions of s square. But the eigenvalue is 1 over 2. the z component, same functions are also eigenfunctions of SC because they commute. They satisfy m sub s times sigma, where m sub s is between s and minus s. Of course, now I have used the symbol s here just to emphasize the similarity between orbital angular momentum and spin angular momentum. For a single electron, s has just one value, small s, which is 1/2. And the ms values, how many ms values are there here? Between, this means ms 1/2 and minus 1/2 in integer steps. So one value for ms is, lowest value is minus 1/2. Add plus 1, what do you get? Plus 1/2. So there are just two ms values. One is minus 1/2, the other is plus 1/2. ms minus 1/2 corresponds to beta. Plus 1/2 corresponds to alpha. All right? These spin functions are assumed to have similar properties to eigenfunctions of any quantum operator. What are they? Eigenfunctions of quantum operators are orthogonal. So here we have two spin functions. One is alpha, the other is beta. Therefore, alpha and beta functions must be orthogonal. So, alpha times beta. Here the variable is spin variable. Call it d tau s, d tau for spin variable, and the integral. Because alpha and beta functions are eigenfunctions of SC operators with different eigenvalues. One is with plus 1/2, the other is with minus 1/2. These two orbitals must be orthogonal, which means the value of this integral is 0. Orthogonality of the spin eigenfunctions. We also assume they are normalized. What does it mean? Values of these integrals over spin variables must be equal to normalized 1. Now, we continue with more than one electron. 2 electrons, 3 electrons, 5 electrons, and so on. We introduce the total spin angular momentum in exact analogy to total orbital angular momentum. Total spin angular momentum for n electrons and the z component. Square of this expression, s square, and sc commute with each other. Remember that each one of these terms contains spin variable for the for that electron. Now, remember whether the Hamiltonian contains spin variables or not. For example, in helium, when you look at or examine this Hamiltonian, what kind of variables do you see here? You have to think about like this. Each electron has 3 space variables plus 1 spin variable. And these 4 variables are independent. Now, in this expression, we do have space variables, but do we have any spin variables here? No. This is important because if you have 2 operators, and if these 2 operators contain different types of variables, do they commute or not? They always commute. So, S square and SC, these contain only the spin variables. But our Hamiltonian does not contain any spin variables, which means both S square and SC commute with H. What does it tell us? Exact solutions of this problem, Schrödinger equation, H psi equals E psi. The solutions of this problem, this means eigenfunctions of H must also be eigenfunctions of S squared and SC. All right? Now, finding eigenvalues and eigenfunctions of S squared and SC is an easier problem than solving Schrödinger equation. So we collect information about eigenvalues and eigenfunctions of S squared and SC and use them in classifying solutions of Schrödinger equation. Similar to the angular momentum, orbital angular momentum, eigenvalues of S square, square of total spin, are S times S plus 1, such that maximum S quantum number here is n over 2. And for a given S, MS values are between plus S and minus S. MS are eigenvalues of SC. And eigenvalues of S square are these numbers. You see, this expression, S times S plus 1, is exactly similar to L times L plus 1. But there is one important difference. What is that? In the case of L quantum number, there is no upper limit for L. But here, there is an upper limit for the S quantum number. Let us have an example to see. Helium atom. n is equal to 2. There are just 2 electrons. What is S max? This number divided by 2, 1. Therefore, allowed S values are, maximum is 2. Now, in integer steps, you subtract 1 to obtain lower values. But you never go to negative values, because such quantum numbers, S quantum number, L quantum numbers, are positive, non-negative numbers. 2, 1, largest is 1, 1 less than 1 is, what is it? 0, and here we stop, because S has to be positive, or I should say non-negative. It may be 0 or any positive value. So the 2 electrons in helium atom, for 2 electrons in the helium atom, there are just 2 possibilities for the total S quantum number. What are they? Either 0 or 1. So if number of electrons here is even number, then it can be divided by 2. In that case, the possible S values are starting with 0, because the maximum is also integers. 0, 1, 2, up to the n over 2. If the number of electrons is odd, like lithium atom, n is 3. In this case, maximum S is 3 over 2. So, what are the possibilities for the total S quantum number in lithium? For 3 electrons, there are 3 electrons here. S quantum numbers, maximum is 3 over 2. Subtract 1 from 3 over 2, what do you get? 1 over 2. If you subtract 1 more, you will go to negative values. So you stop here. So there are 3 electrons in lithium, but again, there are just 2 values for the total spin quantum number. One is 1 over 2, the other is 3 over 2. Number of MS values here. The expression is same as in L quantum number. There are 2 times S plus 1 values for the MS. Let us apply it, even this, to the single electron. A single electron has only 1 S value. What is it? 1 over 2. What are the MS values? Minus 1 over 2 and plus 1 over 2. How many different MS values are there? 2. Now obtain this 2 times 1 over 2 plus 1. You get 2. So it applies, whether it is fractional or whole number, it's always 2 times S plus 1. As in the orbital angular momentum, the energies are solutions of this problem, exact solutions of the atomic Schrödinger equation. These energies are independent of MS, just like they are independent of ML. So here, there is a degeneracy. Number of degeneracy is 2 times S plus 1. In the case of orbital angular momentum, we said 2 times L plus 1. That one is about space degeneracy. This one is about spin degeneracy. These are different types of degeneracies. So, 2 times S plus 1. This is for a given S. Gives the spin degeneracy. Of psi function. All right.